Hi guys, welcome back to our series Intronics Energy. Last time we did a decoder circuit. This time around we are doing an encoder circuit, and the only difference between an encoder and a decoder is that an encoder is directly the opposite of a decoder. Since a decoder transforms information from what computer understands in terms of binary into decimal numbers, what humans understand, then the encoder turns what we understand, the information as we understand it, to what computer understands. So the circuit is pretty simple. It transforms information to binary. That's basically what an encoder does, the opposite. Remember, a decoder transformed the information from binary to decimal, what we understand. So this time around we are doing just a direct opposite of what we were doing last time. And the circuit is pretty simple. You can see it only contains two input, one output OR gates, and some LEDs right there to show you what is happening inside. I've also added LEDs at these points, point A and point B, to show us which binary these numbers are. So if I'm pressing 3, if 3 is on, then the binary will be on to show us 3. So, and the output of those of what we are making today should be in this form, should be in the form of binary. Last time the output was in terms of decimal. Now this time around the output is in form of binary at this point A and B. So if it is 0, if you have pressed 0, then our output at A and B should be 0 0. Both outputs of this OR gate should be off. If I'm turning 1, then B will be on and A will be off, so it will be 0 1 0 1. That's what is going to represent 1. If I'm going to turn, if I turn 2 on, then A will be on but B will be off, so the output will be 1 0 1 0 1 0. Then my last configuration 3, if I turn on 3, then the output here should be 1 1. Both these outputs should be 1. If I'm to write the Boolean expressions of this, the output of these OR gates, this OR gate containing B output will be, it has 1, so it will be 1, or it has 3. That's the Boolean expression. So it will be 1 or 3. Plus in digital electronics means or in logic circuits means or. Yes, and this second OR gate, which contains A as the output, the Boolean expression will be 2. It has 2, or it has also 3. Yes, so that's basically what the circuit entails. It's just a pretty simple circuit. Maybe it's much simpler than the decoder that we were doing. So the circuit is right here. Don't worry about the number of components. Just simple circuit, only that you need this resistors in order to protect your circuits. Also, the OR gates requires some sort of resistors, because the input sometimes have a positive voltage. So if you interchange, or if you interconnect these wires together, like this jumper wire right here, it's going to feed the wrong information. So we need these resistors in order to minimize those errors that might evolve or might come up from this OR gate IC integrated circuit. So my input section is right here. These are the LEDs, 4 LEDs you're seeing on the schematic. Then the switch are right here. So my number 1 switch is going to represent 0. My number 2 switch will represent 1. And my number 3 switch will represent 2. Then my last switch will represent 3. That's my last switch. Then they require this resistors there. The LEDs also require resistors to protect them from the voltages that I'm using. I'm using a 5-volt power supply. You can use any from 3 volts. If it's 3 volts, I think it's not very bad. You can just connect LED direct, but for 5 volts you can blow up the LED. And the output is right here, the A and B. So this first LED will be A, this second LED will be B. So yes, so we will be checking if our output are going to be turning on the way my truth table is there. So I'm going to turn on my circuit, and it's on. Okay, it's on. Let me turn this off. Did turn this switch off? Yes, like that. So my circuit is on. It was 3 was initially on. I forgot to turn it off, so I've turned it off, in order to start with you guys from 0 all the way to 3 for us to understand better. So at normal condition, if I turn on this switch number 0 right here, turn it on. Oh, sorry. If I turn it on, the output is 0 0. Since it is not connected, simply this first input is simply not connected to the integrator. You can see even in schematics, just direct to the LED, showing us that the circuit is on, but if the input is 0, then the binary is going to be 0 0 0 0. So you don't really have to connect the zero part to the IC, because it does not apply in any way. So but next time I'll try to see if there are circuits out there. I'll try to find out if there are circuits out there where you can connect this first input, which is 0, to the integrated circuits for you to get a 0 output. So for now, I've not connected it. So if it's on 0 0, meaning that the binary is 0 0. At 1, if we turn this on, the next one, which is 1, we expect to get a 0 1. This will be 0, this will be 1. So let's check that. I turn this off and I turn number 2 on, then yes, so I get a 0 1 0 1. So B is on, A is off. So that's the binary of 1. Then at 2, we expect to get a 1 0. This will be on, this will be off. So at 2, let me turn this off. We turn on number 2. Okay. Let me try to, okay, yes. So at 2, we get a 1 0, a 1 0, like our truth table right there, 1 0. So that represents 2. Then we go on, the last one, number 3, we should get a 1 1. So we're going to turn this off, and we turn on the last one, which is number 3. I don't know why this is not sticking up properly. Number 3, we should get a 1 1. Yes, a 1 1. So that's a 1 1, meaning that it's binary for number 3. So that's basically what a decoder does. It transforms information from what we understand to what the computer understands. So this section, you can take this section as the input section of a computer. Then this is what the computer does inside. So if this we say this is a keyboard of a computer, if we press 3, then that 3 is taken inside and it transformed into an ACI code. ACI code simply is binary, so it's going to be transformed into binary of what you've pressed. So if it's 3, it's going to read it as 1 1. So that's 1 1. That's the computer language of 3. Yes. So thank you very much, guys, for watching this simple circuit. You can do this at home. If you don't have OR gates, you can make them using transistors. I think I made a video some few months ago on how you can make this logic gates using transistors if you don't have the integrated circuit. So next time we are going to connect an encoder to a decoder to see what they can do. So simply we are going to turn information from what we understand to what computer understands to back to what we understand. So we can say that the information is from the keyboard inside the computer, then to the screen, the display, what we see, what we understand as humans. So yeah, so tune in for that next video.